Hello and welcome to the Tech Brain channel. My name is John Urenda. Your data is valuable, but how do you encrypt it without losing search power? Meet MongoDB Queryable Encryption. Full security, zero compromises. In this tutorial, we'll show you how it works, how to use it, and how to integrate it fast. Watch Folosayo Samuel break this topic down. Over to you, Samuel.
We're going to understand the fundamentals of queryable encryption in MongoDB. Learn how to set up queryable encryption using MongoDB Atlas and Fast API. Explore the implementation of automatic encryption and decryption. Encrypted equality queries work. Configure encryption policies for queryable fields. Implement query patterns for encrypted data. Troubleshoot common query encryption errors. What is queryable encryption? Queryable encryption is a MongoDB feature that encrypts sensitive data yet allows queries on those encrypted fields. It ensures data privacy and helps with compliance, GDPR, HIPAA, etc. Why use queryable encryption? It is used to protect data at rest and in transit, like SSNs and credit card info. It lets you query encrypted data without decrypting first. It supports encrypted equality queries, that is, ND for matching specific values. It also secures data in WireTiger cache and RAM dumps, so it is safe even in memory. Let us break down the technologies we'll be using to implement queryable encryption. MongoDB Atlas. MongoDB Atlas is a fully managed MongoDB service. It offers queryable encryption with automatic encryption. Fast API, which is a modern Python web framework perfect for building APIs that integrate seamlessly with MongoDB. We have queryable encryption components. The data encrypted key, which is DEK, to encrypt and decrypt specific data feed. We have the key vault. The key vault securely store DEK, which is the data encrypted key. We have automatic encryption shared library. This dynamically enables your client application to perform automatic encryption. MongoDB uses libraries to handle query translation for encryption and decryption. We will focus on the automatic encryption shared library. The automatic encryption shared library performs the following task. It reads encryption schema to identify which fields to encrypt or decrypt. It prevents execution of unsupported operations on encrypted fields. The automatic encryption shared libraries does not do any of the following. It does not encrypt or decrypt data itself. It does not access your encryption keys directly. It does not listen for data over the network. This separation ensures that keys remain secure and that only the MongoDB driver handles actual encryption or decryption processes. The MongoCrypt process, it marks specified fields for encryption during read and write operations, ensuring sensitive data remains protected. It blocks unsupported operation on encrypted fields, maintaining data integrity and security. MongoCrypt passes the encryption schema, which uses a strict subset of JSON schema syntax to determine which fields require encryption. If the schema contains invalid syntax or unsupported validation rules, MongoCrypt will return an error. It is equally important to understand what MongoCrypt does not handle. It does not perform the actual encryption or decryption of data using the live MongoCrypt library. MongoCrypt doesn't access any encryption keys directly, ensuring that key management remains separate and secure. It doesn't listen to data over the network, reducing potential attack surfaces. Here's a step-by-step breakdown of how a query is processed using queryable encryption in MongoDB. The process begins when the client submits a query containing a plain text field, like a social security number, SSN. This query is first sent to the MongoDB driver, which is responsible for handling encryption before the data reaches the database. Next, the MongoDB driver communicates with the key management service provider to request an encryption key for the specific field. The KMS providers such as AWS KMS, Azure Key Vault, or Google Cloud KMS retrieves and returns the encryption key securely. With the encryption key retrieved, the MongoDB driver encrypts the plain text field, for example the SSN, into an encrypted ciphertext. This ensures that the sensitive data remains unreadable before it is stored. Instead of storing a plain text, the database will store an encrypted version of the SSN. Once the feed is encrypted, the MongoDB driver sends the query with the encrypted feed to the MongoDB server. Since MongoDB supports queryable encryption, it can process queries directly on encrypted fields without decrypting the data. The MongoDB server processes the query using encrypted indexes, meaning it can match encrypted data without needing to decrypt it. This keeps the data secure even during searches. After executing the query, MongoDB returns the encrypted results back to the MongoDB driver. At this point, the data is still not readable as it remains encrypted. The MongoDB driver then decrypts the results using the previously retrieved encryption key. Once decrypted, the driver returns the plain text data to the client in a readable format. Now, the client gets the correct SSN plain text, while MongoDB itself never sees the plain text value. Let's start with the queryable encryption workflow, which follows a 5-step process. Step 1. Query analysis. When a client submits a query, the driver analyzes it to check for encrypted field. Step 2. Key retrieval. If encrypted fields are detected, the driver requests encryption keys from a customer provisioned key provider like AWS KMS, Google Cloud KMS, Azure Key Vault, or any KMIP compliance provider. Step 3. The driver encrypts sensitive information and sends the query to the MongoDB server, replacing plain text values with ciphertext. Step 4. Server processing. The MongoDB server processes the query on encrypted data using a first searchable encryption scheme without decrypting sensitive values. Step 5. Result decryption. The encrypted query results are sent back to the MongoDB driver, which decrypts the response before delivering plain text data to the client. And just like that, MongoDB enables secure end-to-end encrypted queries without exposing sensitive data. Pretty awesome, right? MongoDB query encryption currently supports two main types of query, which are equality queries and range queries. Equality query allow you to match encrypted fields against a specific value. Range query enable greater than, less than, and between operations on encrypted data. While powerful, there are a few limitations to keep in mind. Number 1. Content factor. It impacts performance when multiple queries target the same encrypted field. Manual metadata collection compaction. This requires additional maintenance. And likewise, encrypted fields map modification. Updates requires extra configuration. And read and write operation support. Some operations may have restriction. Unique indexes not supported on encrypted fields. Topology support limited to replica sets and sharded clusters. So why queryable encryption offers strong security? Understanding these trade-offs is crucial for optimal implementation. To read more on other limitations, you can visit MongoDB official website. To make queryable encryption work, we rely on powerful frameworks, database, and encryption tools. The framework and core libraries, Fast API and Pydantic. Fast API is the backend framework for our application, while Pydantic ensures data validation and serialization. We have the database component, which is MongoDB Atlas and PyMongo. MongoDB Atlas is a cloud database where encrypted queries are executed, while PyMongo is a Python driver for interacting with MongoDB. We also have encryption components, which is PyMongo encryption and PyMongo encryption options. These handle data encryption and decryption. We also have automatic encryption shared library. This enables client-side feed encryption. And lastly, on the encryption components, we have BSON codec options. This provides BSON encoding or decoding. Then we have the utilities. OS manages environment configuration for encryption keys. These tools will work together to create a seamless and secure encryption process while keeping MongoDB performance optimized. Now, let us break down some essential encryption concepts you need to know. Number 1 here is master key. Master key is the primary key that encrypts data encryption keys. In AWS KMS, this is called the Customer Master Keys, CMK, and also KMS provider. This is a service that manages cryptographic keys and operations. For example, AWS KMS, Google Cloud KMS, and Azure Key Vault. Lastly, we have the data key. This is a key generated by KMS that directly encrypts data. It is encrypted by the master key for secure storage and transmission. These key management concepts are fundamental to MongoDB's queryable encryption module. Keep them in mind when designing secure applications application. Let us define how keys are structured within MongoDB Queryable Encryption. This encrypts specific document fields in the database and stored securely in a key vault. Purpose of a key: it maintains detailed confidentiality by encrypting sensitive fields. It enables secure querying by decrypting fields only when needed. Why do we need a key per field? Enhances security by isolating encrypted data per field. If one data encryption key is compromised, other fields remain protected, and it allows granular control over encryption and access permissions. By structuring encryption keys this way, MongoDB ensures strong data protection while maintaining flexible query capabilities. You can find the link to the GitHub repository in the comment section. Now let me explain this code step by step. First, I set up our environment by importing the necessary libraries. The first library there is FastAPI, which is our web framework for building APIs. We also import Pydantic, which is used for data validation. We have the Bison codec option, which provides option for Bison encoding and decode. We have PyMongo, which is the Python driver for MongoDB. And likewise, we import OS, which allows interaction with the operating system. It is used here for generating a local master key. We initialize our FastAPI application. For this demonstration, we generate a local master key. This generates a 96-byte random key. In production, it's recommended to use a key management system, KMS, like AWS KMS, Google Cloud KMS, or Azure Key Vault for enhanced security. We configure our key management service providers. We use a local KMS provider with our generated master key. We define the namespace for the key vault. This specifies that our data encryption keys will be stored in the data keys collection within the key vault database. We set up the MongoDB connection. Replace the MongoDB URL with your actual MongoDB connection string. Ensure that your MongoDB cluster is properly configured. I also initialize the client encryption object. This object is responsible for creating and managing data encryption keys and performing explicit encryption and decryption operations. This access and prepare the key vault collection. We drop the existing data keys collection to ensure a clean slate. In a production environment, exercise caution with such operations to avoid data loss. Ensure uniqueness of key alternate names. This creates a unique index on the key alt names field, ensuring that each key alternate name is unique within the collection. Then generates data encryption keys for the fields we want to encrypt. Each data encryption key is associated with a specific field and is identified by a unique alternate name. To specify which fields in our MongoDB collection should be encrypted, we define an encrypted fields map. This map outlines the fields to encrypt, their data types, associated encryption keys, and the types of queries permitted on them. We have the collection namespace, which specifies the database and collection where these encryption rules apply. Likewise, the fields array. Each dictionary within the fields array defines part. That is the field name in the document. For example, first name. And likewise, the Bison type of the field and the identifier for the data encryption key associated with this field. Then queries, which is an optional list specifying the types of queries allowed on this encrypted field. For instance, query type equality. This permits equality searches on the encrypted data. By configuring the encrypted fields map, we instruct MongoDB on how to handle encryption for specific fields, ensuring that sensitive information remains protected while still allowing for necessary query operations. Next, we configure the auto encryption option to enable automatic encryption and decryption within our MongoDB client. The KMS providers contains the key management service provider details. In this case, our local master key, then the key vault namespace, specifies where the data encryption keys are stored in MongoDB. Then the encrypted fields map, the map we previously defined, detailing which fields to encrypt and how. Lastly, encrypt shared lib path. This is the path to the MongoDB shared library, which facilitates automatic encryption processes. By setting up these auto encryption options, we enable our MongoDB clients to handle encryption and decryption seamlessly without manual intervention in our application code. With our encryption options configured, we can now initialize the MongoDB client to utilize these settings. MongoDB URL, the connection string to our MongoDB cluster, then auto encryption encryption option. The encryption option we set up earlier, enabling automatic handling of encrypted fields. This client is now equipped to automatically encrypt data before storing it in MongoDB and decrypting it when retrieving, ensuring that sensitive information remains secure throughout its life cycle. Before we start inserting data, we prepare our target collection. The first part, drop the collection by removing any existing collection with this name encrypted collection to ensure a fresh start. Then it now initializes a new collection where our encrypted data will reside. Setting up the collection ensures that we have a clean environment to work with, preventing potential conflicts with existing data. To structure the data we've been handling, we define a user model using Pydantic. The user class inherits from Pydantic base model and define the schema for our user data, including first name, last name, and passport number fields, as all as strings. This model ensures that any data we process adheres to the expected structure, providing validation and serialization benefits. To facilitate the transformation of MongoDB documentation in Python dictionaries, we define a helper function. We define a get endpoint to retrieve a user by their passport number. This endpoint enables clients to retrieve user information securely using the passport number as a query parameters. Lastly, we define a post endpoint to create a new user. This endpoint allows clients to add new user to our encrypted collection securely. By defining these routes, we have set up a fast API application that can securely handle user data with MongoDB Queryable Encryption. This ensures that sensitive information remains encrypted in the database while still allowing for necessary operations. Remember to handle your encryption keys securely and follow best practices for deploying fast API applications in a production environment. Now, let me explain how we structure the Docker file. We start by specifying the base image. This set up a Python 3.9 environment, providing the foundation for our fast API application. Here, we update the package list and install the World Wide Web Get, which we will use to download the MongoDB cryptographic library. We then handle the MongoDB cryptographic shared library. We set the working directory to CMP, which is a temporary directory for processing files. Then we use the World Wide Web Get to download the MongoCrypt shared library. Then we use the tar command to extract the content of the tarball. We move MongoCrypt to the user local library to make it accessible system-wide. Then we update the system's library cache to include our new library. We remove the downloaded tarball to keep our Docker image clean. We define the working directory for our application. This sets /code as a directory for which subsequent commands will operate, organizing our application fields. Next, we undo our Python dependencies. We copy requirements text file into the container at /code/requirements.txt. Using pipe, we install the required Python packages specified in requirements text file. The no catch directory option prevents caching, reducing image size. We then add our first API application code. This command copies the entire app directory from our local machine to /code/app in the container. We install the MongoDB shell to interact with our MongoDB instance. Lastly, the CMD instruction specifies the command that should be executed when a container is run from the image. It is important to use the execute form of CMD, which is a JSON array that starts the process directly without involving a shell. This approach ensures that the application receives system signals directly, allowing for graceful shutdowns and proper signal handling. Build the Docker image with the following command. So we have successfully built our Docker image. We successfully start our fast API application. After doing this, visit this spot on your browser to test your application. You can see that our application is running successfully. Now let us test our fast API code. Let us create a user. Let's click on try it out. Add the user first name. Let's say John. Then let's include the passport number. User has been created successfully. We are going to get the user by the passport number. Now let's copy this passport number. Then We're going to paste it here, fetch the user. You can see we successfully fetched the user and our code is working as expected. So it's recommended that you opt for the automatic encryption shared library for more streamlined process. However, MongoCrypt remains supported and can be used if preferred. Here are some common queryable encryption errors with their solutions. The first errors state the encryption process could not locate all required data keys, likely due to misconfigured keywords details. Here are the common solutions. Make sure you verify keywords namespace, confirm key creation, validate the KMS providers, and auto encryption options in your Mongo client configuration. And also the second error, which is encountered when attempting to execute an encrypted equality query without the necessary encrypted equality index. Here are some common solutions. Configure encrypted equality index, verify query type compatibility, review encryption schema configuration, and ensure compatibility with MongoDB version. And also, you might come across this error which states crypt shared library not loaded. This occurs when the application cannot load the crypt shared library, leading to failures in automatic encryption processes. Here are some common solutions. Install the crypt shared library. Download the appropriate version from the MongoDB download center. Ensure compatibility with your operating system and MongoDB version. Configure the library path. Set the crypt shared lib path parameter in your MongoDB drivers configuration to the absolute path of the crypt shared library. Here are some best practices. Replace the local master key with a key from a trusted KMS. Restrict access to the keywords collection. Also use MongoDB Atlas monitoring tools to track encryption related activities. And lastly, ensure PyMongo is up to date. Queryable encryption ensures data remains encrypted throughout its life cycle, in transit, at rest, and in use, minimizing the risk of unauthorized access. It also supports equality and range queries on encrypted data with plans to include prefix, suffix, and substring searches in future release. Queryable encryption assists organizations in meeting stringent data privacy regulations such as GDPR, CCPA, and HIPAA by providing robust encryption mechanisms. Lastly, it allows developers to implement encryption without extensive cryptographic expertise, streamlining the development process and reducing operational complexity. If you found this video helpful, please don't forget to like, subscribe, and share. Thanks for watching.